Hello, welcome to Linear and Nonlinear Systems of Equations. This is using the substitution method. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This lecture is for Math 1508 Pre-Calculus at UTEP. Chapter 7, Systems of Equations and Inequalities, comes to us from Larson's 10th edition pre-calculus text. Section 7.1, Linear and Nonlinear Systems of Equations. Alright, so what is a system of equations? A system of equations consists of two or more equations considered together. Very important, they're considered together. The solution to a system is the single point that is a solution to every equation in the system. Now, it could be that there are more than one point where they intersect, and that depends on whether they're linear or nonlinear equations. Sometimes there is no solution when they do not share a common point. And other times the line may be the same, and therefore every point is a solution. So if we make this go down a little bit, what we're really looking at is if we're talking about linear functions, then a linear function intersecting another linear function, our solution would be the one point they have in common. It is possible with linear equations that they're parallel and there's no solution. And it could be that these two lines, whatever they may be, are exactly the same line, and they're just written differently. Maybe one's in slope-intercept form, whereas another version of it is in standard form. But there's also the possibility that we have nonlinear equations. And so maybe we have a parabola laying on its side, and a linear function. Maybe we have a circle, pretend with me, and a linear function, and maybe a linear function that never intersects the circle. So all of these are possibilities, and solutions are points where these lines intersect. So we have solutions here, solutions any place that they intersect. So we're going to be using substitution method in this lecture. The next lecture I'll talk through the elimination method, and then in the third of this chapter we talk about Gaussian elimination using a system in order to get it solved. So the substitution method, first we solve one of the equations for one variable in terms of the other. So solve for one variable from one of the equations. Step 2, substitute the expression found in step 1 into the other equation. So if you used equation 1, substitute it into equation 2 or 3. To obtain an equation in one variable, we're going to solve that equation. And then once we have an answer for one of the variables, we back substitute into step 1 to find the value of the other variable. And you should always check to make sure the solution satisfies each of the original equations. That's one of the beautiful things about math, is that once we have an answer, most times we can check and we can make sure we're right before moving on. So let's solve by substitution. Here's a system. In a system we frequently have what I call a curly bracket, but I believe it's called a brace. A brace on the left only, saying consider these two together, x plus 4y equals 3 and 2x minus 7y equals negative 24. So in my first step, I'm going to solve the top equation for x. So I'm going to subtract 4y from both sides. I have x equals 3 minus 4y. In step 2, I'm going to substitute that into my second equation. So it's normally 2x minus 7y equals negative 24, but I have another name for x. So we'll call that 2 times 3 minus 4y instead of x. Minus 7y equals negative 24. And you see now that this equation, after we've substituted, has only y values, so we can solve. That's 6 minus 8y minus 7y equals negative 24. Which takes us to 6 minus 15y equals negative 24. If we subtract 6 from both sides, negative 15y equals a negative 30, so y equals 2. Once we have our y value of 2, we can find exactly what x is equal to. X is 3 minus 4 times 2, which is a 3 minus 8, or negative 5. So we'll say this solution, let's put it in red, the solution is the point negative 5, comma 2. Make sure that negative shows up there. So point form, x and then y, just like our normal points, x, y. No matter which one you solve for first, in this case we solve for y equals 2 first, make sure you put them in the correct order. It's not that first one solved, second one solved. It's always x and then y. With 6x minus 3y minus 4 equals 0 and x plus 2y minus 4 equals 0, the easiest one to solve for, I'm going to solve equation 2 for x. And I try to avoid creating fractions when I'm doing substitution. So anytime I have a coefficient of 1 or negative 1, that's generally going to be the variable that I solve for. So I'm going to add 4, subtract 2y from both sides. In the first equation, instead of 6 times x, now I'll have 6 times 4 minus 2y. Still, the rest of it, minus 3y minus 4 equals 0. Distribute. 24 minus 12y minus 3y minus 4 equals 0. Combine my like terms. 24 minus 4 is 20. Negative 12y minus 3y is negative 15y, and if that equals 0, I can add 15y to both sides, divide by 15, and of course 20/15 would be reported as a y value of 4/3. Now that I know y, I could put it back in and solve my equation for x. X is 4 minus 2 times 4/3. We know that 2 times 4/3 is 8/3, and 4 currently has a denominator of 1. So I need a common denominator. In order to get a common denominator, I'm going to multiply both numerator and denominator by 3. Common denominator. So that's 12/3 minus 8/3, which gives me 4/3. And my solution is the point 4/3 for x, 4/3 for y. Make it a 3. There we go. Alright, another example. X minus 2y equals 0 and 3x minus y squared equals 0. We can see that we're into the nonlinear now. Linear equations, always the variables, x and y, have power of 1. Alright, so we don't write the power. Linear functions. So in equation 1, I can easily find x equals 2y. In equation 2, I can substitute. So that's 3 times 2y minus y squared equals 0. Multiply. 6y minus y squared equals 0. But I could easily factor this. Y times 6 minus y equals 0. Anytime I have a quadratic, so a y squared or an x squared, depending on the situation, I'm going to get it equal to 0 in order to solve. So I'm going to use the zero factor property. I get it equal to 0. I factor. And then the zero factor property says that if I have y multiplied by 6 minus y to give me 0, it must be that y equals 0 or 6 minus y equals 0. And if that's the case, then y equals 0 or y equals 6. When I have two possibilities for my y, I have to use each of them to find an x value. So when y equals 0, putting it back in our equation 1, x equals 2 times 0, which is 0. So when x is 0, y is 0. And when y is 6, then x equals 2 times 6, which is 12. So I'll have two answers, 0, 0, and 12, 6, and I'd have to report both of these. Notice power of 2 on y, two answers, not a coincidence. X minus y minus 1 equals 0. I'm going to solve the top equation for y. Couple of reasons for this. One, it's the easiest variable to solve for. I only have to move one term in order to get y by itself. Also, in the second equation, there's only one term that has a y in it, so I'd only have to substitute one time. So that appeals to me as well. We're going to substitute into the other equation. So instead of x squared plus y squared minus 4x equals 0, we'll have x squared plus x minus 1 squared, in place of y squared, minus 4x equals 0. But I'm going to multiply this out. X minus 1 all squared is x squared minus 2x plus 1. And when I combine like terms, I'll have 2x squareds minus 6x plus 1 equals 0. And I can't factor that, so we're going to use the quadratic formula. Using the quadratic formula, I'm not going to go too details. You can see negative b plus or minus b squared minus 4ac all over 2a. And the inside, this is 36 minus 8. 36 minus 8 is 28. Keep in mind that when you're simplifying the quadratic formula, right, simplifying your solutions, you always completely simplify your radical. 28 is 4 times 7, so the square root of 4 is 2. Leave the square root of 7. Simplify the radical completely, and then we can simplify the fraction. Now that I have my radical completely simplified, I can factor out the 2 from the numerator, and I can factor out a 2 from the denominator so that I can cancel them. And I'm left with 3 plus or minus the square root of 7 over 2. Now, if x is 3 plus the square root of 7 over 2, then y, based on our previous slide, which is x minus 1, is 3 plus the square root of 7 over 2 minus 1. That's 3 halves minus 2 halves, which will give us 1 half, plus the square root of 7 over 2. Similarly, 3 minus the square root of 7 over 2 minus 1. That's 3 halves minus 2 halves, which is 1 half, minus the square root of 7 over 2 as well. So 2 points, ugly looking points, but they're points nonetheless with the exact values of x and y. Let's look at some word problems. A small software company invests $25,000 to produce a software package that will sell for $69.95. Each unit can be produced for $45.25. 2 questions here. How many units must be sold to break even? And how many units must be sold to make a profit of $100,000? Now on the surface, this seems like a straightforward problem, but a little bit of unstated work here. Break even happens when cost equals revenue. So we'll definitely need to find a cost equation and a revenue equation. Also, for question 2, the profit is always revenue minus cost. So once again, I need cost and revenue equations. Here we go looking for those. So, a small software company invests $25,000. So this is money they pay out. So that's in the red, right? They have to pay that money to produce a software package that will sell for $69.95. Now this is green. This is money they're making. That's good. Each unit can be produced for, so it costs them $45.25 in order to make it. So, how do I use this information? Look at the question, how many units must be sold? How many units? That's what I want my answer to be. So let's let x be the number of units. We're going to solve for x. So the selling of the product at $69.95 will give a revenue equation, R of x equals $69.95x. You are never guaranteed revenue. All right, there's no fixed revenue, but there is a variable revenue. It depends on how many you sell. The costs to the company include the initial investment and the variable cost per unit. So the amount it costs for each one made. So C of x is 4525x plus 25,000. Break even is when revenue equals cost. Subtract 4525x from both sides, I'll get 24.7x equals 25,000. When I divide both sides by 24.7, I'm going to get x equals 1012.145. And we're just going to go straight rounding on this. 1,012 units will be super close to breaking even. And we're still at a little bit of a loss, but a negligible loss. Think about what this means. The difference in the selling price and the cost to produce is $24.70. This is their net profit for each software package. So they have to sell enough software packages to overcome that $25,000 that they had to outlay as a cost initially. So after 1,012 units, this will now be a profitable company. But how profitable? How many units must we sell to make a profit of $100,000? Well, we know the cost and the revenue functions. And so we can find the profit function by taking revenue minus cost. Notice I put cost in parentheses because I want to make sure I subtract the entire cost function. So again, we'll have 69.95x minus 45.25x giving us the 24.70x, the amount that they actually profit on each software package. But we will have the minus 25,000 because they still have to overcome that $25,000 in initial outlay. So we're going to set this equation equal to 100,000. 100,000 equals 24.70x minus 25,000. You're going to add 25,000 to both sides, divide by 24.70, and you should get 5,060.728. Now, are you going to sell 0.728 of a software package? I know we've all felt like we've bought 0.7 of a software package before, but you're not going to make much money as a company if you sell 0.7. In order to make that profit of 100,000, you actually have to sell that 5,061st unit to cross the threshold of $100,000. So keep that in mind, especially when you're talking about real things. We're not going to sell decimal amounts of them. Alright, so you graduate college and you're offered 2 jobs and you're selling dental supplies because somebody's got to do it. I'm just saying. One company offers a straight commission of 6% of sales. The other company offers a salary of $500 per week guaranteed, plus 3% of sales. How much would you have to sell in a week in order to make the straight commission offer better? Well, let's take a look. The straight commission of 6% of sales, that's C of X commission, is 0.06x, for X being the amount of your sales. The other company offers a salary of $500 per week plus 3% of sales, so the salary position, capital S of X, is 0.03x plus 500 for X amount of sales. So I'm offered two jobs selling dental supplies. I could write functions in order to represent the amount I will have each week. But I want to know, how much would you have to sell in a week? So find X in order to make straight commission better. Commission, we want it to be better than salary, so greater than salary. 0.06x is greater than 0.03x plus 500. I'm going to subtract 0.03x from both sides. Turns out that's 0.03x is greater than 500. And when I divide by 0.03, I'm dividing by a positive, so everything's still good with my inequality. 500 divided by 0.03, that's $16,666.67 of dental supplies that you must sell each week to make straight commission be the better offer. Now, I'm from small town, so that's a little overwhelming for me to sell in a week. If you lived in a big city, I suppose it wouldn't be that bad. But I'd probably take the salary position. You should be motivated. Maybe take the straight commission. Hustle a little bit. Anyway, that's systems of equations, linear and nonlinear systems with the substitution method. Thanks for listening.